with AP Physics C, Electricity and Magnetism. And my name is Kristen Gonzalez Vega, and I am coming from Frisco, Texas. And I have my teacher partner and now friend, Roger.
Hi, Kristen. This is Roger Siegel, and I'm coming to you live from Sarasota, Florida.
Okay, and today we are going to be talking about capacitors and circuits. So today is going to be a little bit of a review. So we've been talking about magnetism and finishing out the content for the year, because colleges really are expecting that you know the rest of the material, even if you're not going to be tested on some of these topics that we're talking about this week. But today is an exception. Today is a tested topic, and we like to put it in here because we're going to be getting into inductors next class tomorrow. And it's good to be able to kind of remember what happens with capacitors and circuits to be able to compare inductors tomorrow with circuits. So today is a review, and today is a tested topic. So if you want, you should probably have some paper handy so that you can kind of follow along with us tonight. We're going to be working through a lot of problems and doing some fun circuits. So again, my name is Kristen Gonzalez Vega, and I am working tonight with Mr. Roger Siegel, and we are going to go through our objectives. After tonight, you should be able to calculate the equivalent capacitance for a set of capacitors, both in series or parallel, or a combination of both. You're going to calculate the potential difference across an arrangement that involves capacitors and sometimes resistors. In addition to that, we'll also talk about the current going through resistors that are with capacitors and circuits. And we're also going to calculate the energy that is stored on a capacitor in a circuit. So those are the things we're going to be able to do. Hopefully those things sound familiar to you. And the first thing I want to go over is just review what a capacitor is. So a capacitor is a way that we can store energy. It stores energy in the form of an electric field. And how it does that is made of two capacitors. So they are separated, sometimes by nothing in between them. Sometimes we insert a material in between them called a dielectric. And I'm going to switch over here. I have a little simulation so we can see that in action. And it's a FET simulation. And on this FET simulation, we have a battery, and we also have these two parallel plates. So these are capacitors. So you can see this capacitor is two parallel plates. And when we connect that to the battery and we close that circuit up, you can see a buildup of charge on each plate. So from that positive side of the battery, we have positive charge building up on that top plate, and we have negative charge building up on the bottom plate. And anytime we have that separation of charge, we go back to what forms in between there, an electric field. And in that electric field, that is how a capacitor stores energy. And so once this is fully charged, what I can do is I also have a light bulb here. And let's also look at, I kind of want to look at real quick here. When this is fully charged, what will the potential difference across that capacitor be? And if we connect it up, we can see that it's 1.5 volts. Negative just because I have those terminals flipped, but it is the same potential difference that the battery has. Okay, so let's now then flip the switch over to the other side. So now we have a light bulb. And when we flip that switch over, now you can see that charge dissipating back out through the circuit, creating a current in that light bulb. And what these capacitors are really good for is they can dissipate that charge, that energy back to the light bulb a lot quicker than that battery can. And so these are good uses for flashes and disposable cameras and other flashes and things that need that energy in a quick little burst. So that's kind of a fun simulation to play around with. And let's go back and look at some more on the power. So if I have this circuit here that involves a EMF of E, a resistor that has a resistance of R, it has another resistor that's in parallel with a capacitor. And I have a switch that kind of can flip either way here. So if in the beginning here, I flip that switch over to A, let's look what would happen. So we're going to flip this, which is going to close this side of the circuit. We're going to get that current going out through the circuit. And so what we do is we can use our loop rule, and let's write an equation that would take us around that loop, relating the potential differences and the currents going through there. So if we use Kirchhoff's loop rule says that any potential difference gains in our circuits have to equal the potential difference that we lose within that circle, or the drops across each element. So we're going to go across the battery, that's a gain. So I would say, well, the EMF of that battery, I could say minus the voltage drop across this resistor. Hold on, let me connect back up here.
Did you get kicked off of your application, Krista? Oh, there you are.
Yeah, but I'm getting right back in.
Okay.
There we go. You can see it, right? Okay, so we've got the EMF of the battery minus the potential difference across that resistor. How could we get that potential difference? It's equal to the current through that resistor times that resistance. And then we also have the capacitor, and we can get the voltage drop across the capacitor because that V is equal to Q over C. And then we get back, and we should come back to 0 there. And so if we then can rearrange this, and we think about at time 0, what would be the charge when we first close the switch? What would be the charge that has built up on the capacitor? Well, when we first close the switch, there is no charge on that capacitor. So this becomes 0. And so really we can say at time equals 0, when there is no charge on that capacitor, the EMF of the battery is equal to IR. And so we have that maximum amount of current going through that resistor. So when we first close that switch, that light bulb is going to be really, really bright. And so how does that capacitor act? Well, that capacitor really is kind of behaving like a wire. It's almost like it's not even there because there's no charge on it. And so we have that maximum current going through that light bulb. But as that charge starts to build up on our capacitor, well, then what's going to happen to that current going through the resistor? If we look back at our loop rule, if that charge is now increasing, well, that means that current going through my resistor has to be decreasing. And so that light bulb is going to get dimmer and dimmer and dimmer until it finally shuts off when there is 0 current going through that resistor. And we're going to derive these relationships and write the differentials another day. Today, we're really just going to look at those steady state behaviors. So kind of like right when we flip that switch, what can happen in our circuit? And then after a very long time, when that capacitor is fully charged, again, kind of what's happening in that circuit. And we'll get to that in between a little bit later. So after a long time and that charge is building up and that capacitor is fully charged, there's no current going through the resistor. And so that means that we have kind of like an open switch. So we can kind of characterize the behaviors that when at time 0, a capacitor always behaves like a wire. And this is something you kind of want to memorize or just commit to your head there. Like at time 0, when we close the switch, that capacitor is like a wire. And how would that then behave and the rest of the circuit behave if that were a wire? And after a long time, we treat it like it's a break in the wire or it's an open switch. And again, look at the rest of that circuit. If that were an open switch, how would the rest of that circuit behave? So now let's look at what happens now we have that capacitor fully charged. And when we have that capacitor fully charged, kind of like in that simulation, if I flip the switch over here to B, well then that charge is going to dissipate back out through the circuit and there'll be a current now through that resistor. That energy is going out through there. And so again, if we look at that loop rule, well, the potential difference across the capacitor, which is equal to Q over C, is going to turn into the voltage drop across the resistor. So we can look at some of those relationships as well. So we can kind of power that light bulb by discharging that capacitor. Okay, so I'm going to turn it over to Roger, and he's going to go over some examples with us and what happens if you have multiple capacitors. Let me stop my share here. It's all yours, Roger.
All right, well, thanks. Great job. So now we're going to look at some problems that are going to help us understand what happens with capacitors. Again, when right after we close the switch and we start charging the capacitor, what happens in a circuit. And then over time, as the capacitor charges up and it becomes like an open switch, it acts like an open switch, then what happens? And so that's called the steady state occurrences. And I'm going to go ahead and share my screen with you. And I'm going to start here on our OneNote. And so let me hit share. And so I think you guys can see that. Okay. And excellent. So let me get to the appropriate place here. And we want to look at this. Now, I love doing problems like this. These are some of my favorite ones. And these are how we treat capacitors when they're in series and when they're in parallel. So if you remember from the work we've done before, all right, let me see, is that working? Okay, great. So when two capacitors, let's look at these capacitors. So you can see that we have, says each capacitor has capacitance of 4 microfarads. What is the equivalent capacitance between X and Y? So here's our X and here's our Y. And we want to know what is the total capacitance or the equivalent capacitance. Each one is 4 microfarads. Okay. Now, what are we going to do first? Are we going to first treat this as a series or first treat this as parallel? Now, when you're simplifying circuits, either with resistors or with capacitors, you go from the inside out. You take the smallest parts and you start to simplify them and you build out and you add and add and add until you just have one simple circuit. So let's go ahead and draw this little arrow down here. And let's try another circuit. And what I'm going to do in this other circuit is I'm going to combine these two here. And I'm going to combine these two here. And so this is still my point X. Okay. And now I'm going to have one capacitor here and one capacitor here. And there's my point Y. Now, what did I do to bring these capacitors together? And so, or maybe the more appropriate question is, how are these capacitors mounted? How are they hooked up so that I can join them? And I hope you could see, remember that these are parallel capacitors. And so for capacitors that are mounted in parallel, which you can see they're kind of mounted one to the other here, one to the other. I mean, it's a parallel nature. That CP is equal to the sum of Cn or C1 plus C2 or C3. In other words, we're going to add those together. And so what we have is 4 microfarads plus 4 microfarads. That's going to give me 8 microfarads and 8 microfarads on that. Okay, so that's our first simplification. Okay, we're deconstructing this, right? And so the next thing I'm going to do is I'm going to say, all right, well, now how can I bring these two together? All right, how can I make that into one? Okay, and so there's my X, there's my Y. And so you ask, okay, well, how are these two mounted, right? Because when we went from here to here, we said these two are mounted or hooked up in parallel. These two are one right after the other, and that's in series. And so our formula for series is 1 over C equivalent in series is 1 over C1 plus 1 over C2 plus 1 over C3 plus ... And so again, this is the parallel up here, and this is series, and these two are in series. And so that means that 1 over C equivalent is 1 over 8 microfarads plus 1 over 8 microfarads. And so 1 over C equivalent is 2 over 8 microfarads. The microfarads are in the bottom there. Or C equivalent is equal to 4 microfarads. So the answer to this question is that these 4 together equal one of them alone, which is a kind of tricky thing that physics teachers sometimes try and do with problems, is silly things like that. Probably something that an electrical engineer wouldn't do, but they don't have as much fun as we do. All right, so there's that one, that's the first one. I want to do two more problems with you. This one here is an RC circuit. RC circuit stands for resistor and capacitor. And so here's our circuit. I'm going to take a sip here. Thank you. And it says here that the EMF, that script E stands for EMF, which is another way to say voltage, you can see is 9 volts. And so we have a 9-volt battery here. And we've got a switch here. We've got capacitor 1, which is 1 microfarad. And I'm not going to write the value of this capacitor because it doesn't become important in this problem, but it certainly is something we're given. Each of these resistors is 3 ohms. Okay, so we've got 3 ohms here and 3 ohms here. Sometimes OneNote does that to me. Especially if I try and draw something really tiny. All right, so 3 ohms, 3 ohms. And so the first thing is at t equals 0, or I would say right after t equals 0, you know, like right after I close the switch, right here, close the switch, find the current through RA and RB. Now, when, and of course, something we would start with is we would say that this is an uncharged capacitor. And I'm sure you assumed that, but we got to say no charge on that capacitor. Now, an uncharged capacitor, when you start to apply a potential difference across it, at the instant, it acts like a closed switch. And then slowly, as it charges up, it starts to act like an open switch. And it goes from letting a ton of current through to letting no current through. And so we're going to look at the initial point when it acts like an open switch, a closed switch, and then the final point when it acts like an open switch. So we're going to look at this. Let's look at this circuit here. Now, when I first close the switch, again, this is now like a closed line here. And what that means is that the current is going to move. I'm going to go ahead and get another color here. The current is going to move around this circuit, and it's going to go exclusively in this loop. And it's going to totally bypass RB. And the reason that it's going to totally bypass RB is because when I first close the switch, there is no resistance here. And so basically I have shorted out this resistor only for a second, just for the first second, okay? So now we can tell you, if we want to know, find the current through RA and RB, over here, I'm going to say here, RB is equal to 0. There's no current through it because I've shorted it out. And what about RA? Let's go over here. I'm going to come up here and do some work with RA and see what that current is. All right, I'm sorry, that's the current through RB, not RB is equal to 0. All right, now RA, let's go find the current through RA, and I is equal to V over R. So when I first close the switch, I've got 9 volts, and I've got a resistance of 3 ohms, and so that's going to give me 3 amperes, okay? And so RA is equal to 3 amperes, 0 and 3 for the first part, okay? Now, let's go ahead and look at the second part. I'm going to go with green on the second part. Now, on this one, remember, this is now a long time after the switch has been, this switch has been closed, and now this does not act like a closed switch, it acts like an open switch, like there is no current going through here, not like, there isn't any current. So I'm going to try and erase this here. Let me see if I can do that. There we go. There is now no current, okay, going through this part. And so what we have is we have the current, and let me get a thicker line here, and we've got the current going this way and this way. In other words, if I want to just real quick draw that circuit, what I have is a resistor here, a resistor here. So it's a simple 2 resistor circuit. Now when I have these two resistors together in series, right? This is 3 ohms and this is 3 ohms. When I've got those together, that's going to give me 6 ohms. Okay, and so I'm looking for the current here. So I is equal to V over R. and that's going to be 9 volts over 6 ohms. Let me move up here. 9 volts over 6 ohms. And so that's going to be 1.5 amperes. And now you might say, well, 1.5 amperes, notice that's these two resistors are in series. That's 1.5 amperes through each resistor. And so IRA equals IRB equals 1.5 amperes for a long time. And that's what we call a steady state problem. All right. Now, one more to do. And this is also, I hope this one takes you back. This is really old school. I know you guys love these problems. I love doing problems like this with circuits and taking the circuits and making them simple and then complex. And so we're going to do that. All right. Now, what I've got here is, you can see I've got this problem set up, and it says for t equals 0, again, t equals 0 when the switch is closed, what do we have? All right. Now, when the switch is, again, first closed, that right after, or t is infinitesimally greater than 0, we have the current, and it's going to, remember, flow across here as if that were just a wire. That's the way it's going to be at first. So we are going to look at these things. We're told that this is 10 ohms, this resistor. This resistor is 30 ohms. Oops, if I go too slow or if I go too small on that, things happen. And this resistor over here is 60 ohms. All right. So I've got all this. I've got 36 volts. My EMF is 36 volts right there. And so now I want to figure out what's going on I want to find the resistance. Well, the resistance is given. I don't need to find that, but I will find the equivalent resistance. I want to find the current, the voltage drop across each one of these, and I want to find the power dissipated in each one of these objects. Okay. So the first thing let's do is we're going to decompose this circuit, which means we're going to take it. It's got effectively 3 resistors, and we're going to break it down into two resistors and then into one. So the first thing I'm going to do is I'm going to come over here, and let me make this a little bit bigger. Okay. And the first thing here. All right. First thing that I want to do is I want to go ahead and draw this. We've got this one, okay, 10, 30, and let me come down here, sorry, with that, okay. Try again. Okay. Oh, I did gray instead of green, sorry. Okay, now that one, notice the only thing that I did is I took the capacitor just out of the system, out of the equation, because it is not part of the problem at this point. So I'm going to leave it alone. Now, the next thing I'm going to do is I'm going to now, and I have to go back to the green, sorry. Okay, I'm going to now break this down into simpler components. So I'm going to, usually I start far away from the battery. And so that's over here. And so this is 30 and this is 60. And so I know that to find the equivalent resistance of that, we're going to say 1 over 30 plus 1 over 60, because these two are in parallel. You can see that each one is attached at this point and they're attached at this point. So they're attached to both sides of each other. They're in parallel. And so what that means is we have, that's 2 over 60 plus 1 over 60, or 3 over 60 is 1 over R equivalent, which means that R equivalent is equal to 20 ohms. So these two together in parallel are now going to function as 20 ohms. So now I'm going to draw a new circuit here, and I've got, let me back that up a little bit, and I've got the, here I've got the, oh, I did it again. Oops, I did it again. Try it. Okay, I've got the 10 ohm resistor here. And now I've got this 20 ohm resistor, which is really just the equivalent resistance from these two. And so of course that, I don't think I have to draw that one out. That's 10 plus 20 because they're in series. And so when resistors are in series, we add them simply. And so this is now a circuit, a simple circuit with 30 ohms of resistance. All right, now, and 36 volts. Now we can start to work backwards and see what we can learn and put it back in the table. Now, the first thing I can figure out is that the resistance, my equivalent resistance, I said, is 30 ohms. Okay, and that means that I can find the current, and I is equal to V over R, okay, which is 36 volts over 30 ohms, and that's 1.2 amperes. So I'm going to put a 1.2 amperes there. Okay. Now, I'm going to work backwards using the potential difference. I can now, and I'm going to switch to another color so we can kind of see how I work backwards. I can find the potential drop across each one of these circuits because I know that this is 1.2 amperes through the main branch. And so V is equal to IR, sorry. And so that's 1.2 times 10 or 12 volts. So that means that there is a 12 volt drop across RA. This is a 12 volt drop. Now, if I have a 12 volt drop across here and a 36 volt gain, that means that my drop here has to be the difference, because according to Kirchhoff's loop rule, when I go around a loop, the sum of the voltage gains and drops has to be 0. And so plus 36 minus 12, this is going to be 18 volts. Now, this is my fictitious branch over here because there's nothing with 20 amps, 20 ohms in this whole circuit. But guess what? That's what, these are in parallel. And remember, branches that are in parallel always have the same voltage drop across them. So that means that this is 18 volts as well. And you could look at Kirchhoff's loop rule. This is, if I'm going this way, this is an 18 volt drop, and that would be an 18 volt gain. So around any closed loop, we have a sum of 0. And so now I can go ahead and find the current through each part of these. Now, I already know that this is 1.2 amps because that's the main branch. Okay, we already found out that's the 10 ohm. What happens when the current, oops, sorry about that, that does happen. What happens when the current, which is 1.2 amperes, going this way, what happens when it gets to this junction? Well, that's a different Kirchhoff's rule. That's Kirchhoff's junction rule. And that tells us that the sum of the currents entering and leaving any junction has to be, has to sum to 0. The sum of the currents entering a junction has to equal the sum of the currents leaving the junction. And that's an articulation of the law of conservation of charge, because you can't invent charges, otherwise they would have to leak out or something. So if this is 1.2 amps, I can come back here and say, what's the current through one of these? All right, well, I'm going to do that over here. And so I is equal to V over R. Okay, and so we have 18 volts. Okay, and let's put that over 30 ohms. Okay, and you can see that 6 goes into 18 3 times, and so that's 3/5 or 0.6. And so what we have there, I'm sorry, that's incorrect. 3/5, yes, 0.6. So this is my mistake. I am so sorry. This is my mistake. This is not 18. Please bear with me. Okay, let me go back and fix this. Aha. What is 36 minus 12? It's not 18. It is 24. Of course. Okay, got to check my notes. Sorry about that. So this is 24 volts divided by 30. And that's going to be much better, 5/6. Okay. And so that what we have here is we have 0.8 amperes. And if I have 1.2 amperes, 0.8 amperes going this way, what do I have coming this way? And that's going to be 1.2 minus 0.8 is going to be 0.4. And so that's going to be 0.4 amperes. Okay. Now, the last thing that we want to do is look at power. And power, remember, is there's 3 formulas for it that will be on your AP exam. P is equal to IV. It's also equal to V squared over R and I squared R. And it's worth it to just have those guys in your back pocket. All right. So when we come here and we multiply the current times the voltage, 0.4 times 24, we get 9.6 watts. When we multiply our current here, 0.8 amperes times 24, we get 19.2 watts. Oops, 0.2 watts. When we multiply the 1.2 times the 12, we get 14.4 watts. And when we add all those together, we get 43.2 watts, which is also the product of these two, current and voltage. Wow, do you remember doing those tables? I'm sure you do. So I love doing that. That's a lot of fun. Don't worry about that if that felt a little rusty, because before your exam, we're going to do a whole review session on circuits, but we wanted to bring you back to them. I'm going to send you back to Frisco, Texas, and Kristen's going to take us home.
All right, thanks, Roger. They kind of remind me of doing puzzles or like filling in Sudokus when you're doing those tables. So we're going to look at one more problem, and we are going to do a problem from last year's exam. And you can find it if you want to later. It is on the last year's exam, but it's set 2 of last year's exam. And it's question number 1. And it's this: we have a circuit represented above composed of 3 resistors. One has a resistance of 2R. Well, 2 of them have a resistance of 2R, and one has a resistance of R. The voltage of the battery is V naught, and we have a capacitance C on our capacitor. Also, there is a switch. We're going to close that switch, and after a long time, that circuit is going to reach steady state conditions. So this now we're talking about after it already reaches those steady state conditions, not those initial ones, those kind of after a long time. Answer the following questions in terms of the potential difference of the battery, R, C, and fundamental constants. So the first part is we want to derive an expression for that steady state current supplied by the battery. So in order to find that current from the battery, well, let's think. How does a capacitor act after a long time? Once we have reached that fully charged steady state behavior, the capacitor acts like it's an open switch. And so when we get to inductors, they have a different symbol too. And one thing I tell my students is that inductors and capacitors behave how they look after a long time. So how does a capacitor look after a long time? Well, it looks like a gap in the circuit, right? So it acts like an open switch. So the only thing that we're really going to be looking at then is our loop around the circuit this way. And if we apply our loop rule again, well, then we can say that the potential difference from the battery V naught minus the IR through resistor 1, which is 2R, minus, we're going to go across that resistor here, which is going to be another IR, and that resistor is just R. And we get back, that's got to equal 0. Well, since we're looking at this one loop, we know that current is going to be the same there. And so really I can say that V naught is going to equal I times 3R. So then that steady state current from the battery is going to equal V naught divided by 3R. So that would be that current after a long time that is being delivered by the battery. Okay, part B says to derive an expression for the charge on the capacitor. So even though that capacitor is acting like an open switch, that doesn't mean that it doesn't have a potential difference across it or that there's charge. Like it's fully charged. And so just that capacitor charged, it's got a potential difference across it. And what could we say that that potential difference is? Well, if this is acting like an open switch, we know that the current through this guy is going to be 0. And so if we were to take this outside loop, well, the only potential difference we would have is that drop across the capacitor. And so that capacitor potential difference is going to be the same as the potential difference across that resistor in the middle. So I can say, if I go over to the side here, that the potential difference across the capacitor is going to equal the potential difference across that resistor R in the middle. And then we can go about finding what that potential difference across that resistor is. And so if we look at that one, since they're in parallel, they have the same. So we can go back and rewrite our loop rule. And so I now know that I can say that V0 from the battery is going to be equal to, well, we can go back to this loop here now, and we can say that we now know the current through that one is equal to V0 over 3R times that resistance, which is R2R, and then plus the potential difference across the resistor here, which we're just going to call VR, because that's really what we want to know. If we know what the potential difference across this middle resistor is, the same potential difference across the capacitor. And so we can say then that my VR is going to be equal to the V0 minus my, if I can combine these, the R's are going to cancel, and I'm left with 2/3 V0. Well, what is V0 minus 2/3 of V0? Well, that leaves us with that voltage across the resistor, which is also the voltage across my capacitor, is equal to just 1/3 V0, or V0 over 3. That's going to give me the potential difference across that capacitor. Now, how can I use that to get the charge? Well, again, we know that the potential difference across the capacitor is equal to Q over C. So then we can say that my Q is equal to the voltage times the capacitance. And so then the charge is going to equal V0 over 3 times C. And that would be our equation for the charge that's stored on that capacitor. Okay, let's go back and look then at the next part, derive an expression for the energy stored in the capacitor. And so on your formula chart, you have a couple of different equations for the amount of energy that's stored in a capacitor. So I'm going to write them both down, and then you kind of have to decide what you know, what you don't know, and which one to use, right? So we know that the energy stored in a capacitor is equal to either 1/2 Q times V, or we can say it's also equal to 1/2 CV squared. So if we look at what we can have our answer in terms of, we can't have our answer in terms of Q because it's V0, R, and C. Now, maybe I could go in and plug in that Q is V0 times C over 3, and you could solve it that way. Or we could use this one right here. So this is the one that I went with. So we know that the energy stored on the capacitor is 1/2 C, which we know the capacitance of that is just C. And we know the voltage drop across that, the potential difference of that capacitor, is equal to V0 over 3. Okay, so, but this is squared. And so then if we go ahead and solve, then we square both those, we get over 9, V0 squared over 9, 1/2. So this becomes C times V0 squared over 18 is that energy that's stored in the capacitor. Okay, and then the last part is write but do not solve a differential equation that would relate the charge as a function of time on the capacitor. So whenever we're doing these, and we're going to solve this, again, we're going to go back and actually set these up and solve them when we're talking about capacitors and circuits in our review. But we're going to go through and set it up. And the way that we want to set these up is we're always going to use our loop rule. And so after this long time, if we go around and we look at just the loop here, because now the switch is opened, right? So the switch is opened at time 0. So I'm going to rewrite my circuit up here. It is opened. All we have at middle resistor R and our resistor here that is 2R, and my capacitor once that switch is opened back up. And so now if we go through and write our loop rule, well, now we can say that the voltage, where's the voltage drop initially? What is supplying that potential difference to the circuit? It is the potential difference of the capacitor. So we can say that the potential difference of the capacitor is going to be equal to the drops across those resistors. So if we say I times R plus I times 2R. And so I can simplify that and say the potential difference across the capacitor is equal to I times 3R. Now that isn't a differential yet, but that's how we always want to start it. We want to write that loop rule, and then where could we plug in a differential? Well, I can say that the potential difference is equal to, well, that's Q over C. But I want to say that it's any charge over the C as that function of time. And then I can say, well, instead of current, I can say that I is dq over dt. I'll have to excuse the space here, right? Still times that 3R. So I'm going to rewrite that over here. We can see it a little bit better. We can say that R q over c as a function of time is equal to my dq over dt times 3R. And on the AP exam, they are not picky about the signs always. This year, they weren't picky about the sign, but we know that one of these is a positive potential difference, right? And the other one is negative. But this, we can say that the amount of charge that the capacitor is losing is equal to that flow of the current that's going back through. So truly one of those sides should be negative. Okay, so that would be our practice for today. So to wrap it up, you should now be able to find what the equivalent capacitance of the capacitor is, right? They behave opposite of what resistors do. So if they are in series, we have to do the 1 over the equivalent capacitance. And if they are in parallel, we can simply add them up. We were able to find potential difference and current in a circuit that has a capacitor and resistor in it. We found the potential difference in the capacitor in an arrangement and the energy source. And then we found the charge stored on the capacitor also. So that is all we have for today. Thank you so much for tuning in. And we will see you tomorrow to talk about inductors and circuits. Right, Roger?
Yeah, thanks for tuning in. Can't wait to see you tomorrow night.
All right, you guys have a wonderful night.